when we look at intermolecular forces, that's results on phases of matter, okay? Phases of matter is your solid, liquid, and gas. If we did not have solid, liquid, or gas, what would happen is that you would not have different phases. Um, Finally, it loaded on my iPad, so let me go ahead and do a slideshow. Apologize for that delay. So here we have a picture of a solid. Solids are where the chemicals are highly organized. They're sticking to each other. They're kind of like, there's a certain glue that holds one molecule near another. Okay, it's not the bonds, it's what we call intermolecular forces. You can loosen that glue by heating it up, by applying energy. And as you loosen it up, these molecules will loosen its hold from one another, and you get, see how we're applying heat? You get to the liquid form. And then if you add more energy, more heat, then you can actually separate it into its gas phase. And so again, that glue is what we're going to be studying. That glue is called intermolecular forces here. If you cool it down, then the glue becomes significant, and then it holds the matter together. So that's what you see when you go from a gas to a liquid. What's going on is that the gas are totally separated. The molecules in the gas are totally separated. They bounce off each other, but they don't stick. When you cool it down, then they start sticking because the glue becomes more significant. And then as you cool it down even further, then it sort of holds it in place. This is a heating cooling curve, and I think we saw this back in chapter 3. It tells you about the phases of matter. And here, what happens is that we have the solid phase. And that's because the glue that holds matter together is very strong. At low temperature, it's very strong, they're very significant. But as we apply heat or we apply energy, then we loosen that glue and we get these things separating from each other, okay? You guys remember, you guys had the heat capacity, the specific heat. You guys did an experiment on that. And that's the amount of heat you need to put in order to like get a phase change or to raise the temperature. So whenever you're raising the temperature, you're applying energy to make those chemicals vibrate more. It'll vibrate to such a point that a solid will start to melt, and then it gets to the liquid form, and then the liquid will start to boil, and then it'll get into the gas form. Okay, but the key here is that there is a force holding one molecule to another, and that force is called intermolecular force. And that intermolecular force is not just one type of force, it's actually different layers. If you remember when you were, say, in grammar school, or maybe you guys have kids, they probably introduce you to that paste, that white paste, and some kids, they tend to eat it, okay? I don't know why, but they do. But if you think about that white paste, you can put it in construction paper, and then over time, it actually peels off. It's a very weak type of glue, okay? Then maybe you graduated to middle school, and then they trusted you with Elmer's glue. Well, Elmer's glue is a lot stronger. It's different from paste, but it's still a glue. When you put two things together, you could probably work to pry them apart, okay? But it will require more energy. And then maybe you go to a shop class, and they give you this super glue or this some putty, a Bondo putty or fiberglass, where it's really, really hard to pry apart. But if you work, it will pry apart. That's the same thing in terms of intermolecular forces. In intermolecular forces, you have these different layers of glue that are applied to matter, and as you heat it up, you start peeling off the different forces that holds matter together. You overcome them, and it's like peeling off the different layers of glue that matter will have. So that's the analogy I want you to think of when we're talking about intermolecular forces. Okay. Here again is a illustration of a solid, liquid, and gas. And what's going on again? It's highly organized right here. As we apply heat, then they loosen up because the traction between them is less. And then as we apply even more heat, there are no attraction. In the gas phase, the chemicals are without intermolecular force between them. And so if we didn't have intermolecular force, then everything would be in the gas phase. This right here is the water molecule, and there's a bunch of water molecule in space, and you notice how it's very organized. It doesn't look organized at some orientation, but it's very organized in other orientation. You notice that space in between the water molecules? Well, that's the void space when it converts into a solid. When it converts into a solid, it maximizes intermolecular forces like that. And you have this big hollow space, tubes, in between this architectural structure. So we're just doing a different perspective of water so that you can appreciate what's going on here. The more important thing is that when we take a solid and we start heating it up, look at the edges. The edges is the first thing that will melt, and then it becomes more random. We're breaking up the forces holding one water molecule near the other. But you notice how now that when we're heating it up, it becomes more random. And so the space in between is not there anymore. So that's why the volume between the solid phase of water and the liquid phase of water decreases, because now the water molecule can sit on top of each other. And that's what you see right here as we're taking ice and we're melting it. Let me go ahead and fast forward this so that you guys can see what's going on until finally it's totally melted. Of course, when it's in a solid like that, you notice how there's huge void space in between. That's why the solid form of water has a bigger volume than the liquid form of water. So that's what happens at the atomic level. So let me go ahead and go back to the slideshow. And so as I was saying, the intermolecular force is the glue that holds one chemical to another. But you have to make sure you distinguish that from intra. Intra are the bonds that holds one atom to another. And the intramolecular force are covalent bonds or ionic bonds. That's holding the integrity of the chemical together. That's why they have that structure. The intermolecular force keeps one chemical near another through these different types of glue. Okay? They're between, just like we have an interstate highway that goes between states. Well, intermolecular is between chemicals. Intra is within. So there's a difference there. So the two types of intramolecular force, like I said, ion, that's ionic bonds and covalent. There are four types of intermolecular force. This is the different layers of glue that I talked to you guys about. One is called ion dipole. So if we have an ion, like sodium ion, okay, and we have a chemical that's polar, like water. See how water has a partially negative here and a partially positive here. Well, that partially negative is going to be attracted through these little dots that I've drawn to the sodium ions. And that's the mechanism by which salt dissolves in water. When salt dissolves in water, what happens is that the polar water molecule actually pries the ions in the crystal structure of sodium chloride. So this would be a sodium and this would be a chloride, but it basically pries this and pulls it apart, and it stabilizes it by the water molecule. And so how do we designate that? We designate that as NaClAq. AQ meaning that the water is hydrating those ions and allowing it to dissolve. That's an ion-dipole interaction, okay? Ion is attracted to a polar chemical like water. Of course, if the chemical is non-polar, like oil or gasoline, those chemicals are non-polar, salt's not going to dissolve in non-polar because there's no incentive to be yanked apart from its lattice. It'd rather be hanging out with the negative chloride than go with a non-polar chemical. That's why you can't dissolve salt in oil or chemical that's non-polar, because there is no mechanism for that. Then we have dipole-dipole. And remember, you guys know how to determine whether a chemical has dipoles. We look at the distortion of the chemical. We determine whether the chemical is polar or non-polar. Well, that's why you need to know whether the chemical is non-polar, because dipole-dipole, let's say we have a partially positive here and a negative here, that's going to attract another chemical like magnets. Like magnets. Opposite attracts. And so that's the mechanism by which something dissolves, okay? When you put a water molecule next to each other, the water molecules will orientate itself so that the partially positive end of water is going to be attracted to the negative end of another water molecule. That's dipole-dipole. Then there's something called dipole-induced dipole. So if a chemical is polar, okay, and a chemical is non-polar, then there is that type of interaction as well. I'm not going to say much about this. You guys will learn more about it in Chem 200, but that's how oxygen, which is a non-polar chemical, dissolves in water. Even though water is polar and oxygen is non-polar, you can still get oxygen in water, okay? Otherwise, we would not have marine life. Fishes that lives in the ocean actually extracts the oxygen from water. But what happens is that every once in a while, the electrons on this oxygen will be attracted to the partially positive part of the water molecule. And so what that happens is that it creates a dipole within the nonpolar chemical. That's why it's called dipole. This chemical is polar. Induced dipole, because it creates a dipole by inducing it. Okay, let me clear that. And then we get something called induced dipole. And I'll explain that later on, but it's basically how one nonpolar chemical is attracted to another nonpolar chemical. And there's a mechanism that's involved in that, okay? So let's take a look at the strength of these intermolecular forces, and it's not black and white, not black and white. In other words, these things do not have crisp borders. They overlap each other. Ion, the range is between 400 and 4,000 kilojoules per mole. Covalence between 150 to 1100. So you've got certain ions that are weaker than covalent, even though in general, it's a much stronger type of intramolecular force than covalent. But again, there's overlap here, okay? And then these are the different types of intermolecular. So this is intra, these are inter. And notice that ion dipoles certainly up there, 60 to 600 kilojoules. Right here. Dipole, it's the next strongest. So if we have if we think about energy and we're thinking about ion dipole would be like that, maybe 40 to about 600. Dipole, on the other hand, is between 5 and 25. That's dipole, DD for short. Then dipole-induced dipole is between 2 and 10. So there are instances where it overcomes, 2 and 10. Let me erase that. Make sure, oops. That's your energy. Okay, we're looking at, say, 40 to 600. That would be ion dipole. Dipole would be between 5 and 25. And then dipole-induced dipole would be between 2 and 10. And then London dispersion force is between 0.5 all the way up to 40. So in other words, even though London dispersion force may be the weakest, in some cases, it actually can overcome dipole. Like I said, it's not black and white. There are overlaps. That's why I wanted to give you this illustration, so that you know that there are ranges by which these glues are going to be stronger, even though in general it might be weaker. The weakest would be London dispersion force, but there are examples in which the London dispersion force overcomes the dipole force. Okay, that's basically what I'm trying to say here. So all these lends themselves to properties like the boiling point. When a chemical has very, very strong glue, very strong intermolecular force, then it's very difficult to pry them apart. So it would need a higher boiling point. Okay, so chemicals that have high boiling point generally will have a strong intermolecular force because it's difficult to pry them apart. Likewise with their melting point. If they're held together by strong intermolecular force, then you need a higher temperature to pry them apart. So in general, the stronger IMF, intermolecular force, the greater these properties. Properties like melting point, boiling point, heats of vaporization. Heats of vaporization is the amount of energy you need to pump in to vaporize a substance. That's different from the boiling point. The boiling point is the temperature you need to create that substance to vaporize. Heat of vaporization is the energy that you need. Temperature and energy are not the same, but they are certainly related. Okay. Specific heat, and heats of fusion, that's the amount of heat that you need in order to melt a substance, or the amount of heat that you need in order to raise the temperature. Again, if the intermolecular forces are strong, these things will all be high. Heat capacity, that's the energy that you need to raise 1 gram of substance 1 degree. Okay. Remember, specific heat is the energy you need to raise any substance 1 degree. Different properties. Here's an example of what we're talking about. Talking about specific heat, heats of vaporization, heat of fusion. So go back to chapter 3 and take a look at that, and remind yourself about these properties. Surface tension. Surface tension has to do with how these chemicals at the surface are attracted to its neighbor. When it does that, it creates a tension at the surface. And so you can actually float a metal on top of water because water has a very strong surface tension. Capillary action. Capillary action is the cohesive force that allows the molecule to stay together, but also the adhesive force that allows the water molecule to be attracted to glass, because glass is made out of silicon oxide. So the oxygen is attracting the water molecules. That's why it has this capillary action. That's why you can have colored flowers if you put food dye in water, because of the capillary action in the stems of plants. And you can do this experiment if you want, okay, which we do. And that's the reason why trees hundreds of feet up in the hundreds of feet tall can actually suck water from the ground because of capillary action. Okay. Viscosity, you guys can read about that. That's basically the energy for this particular substance, resistance for a substance to flow. There's actually viscosity tests out there. What they do is they take these chemicals, they put it in a graduated cylinder, and they take a ball bearing, and they figure out, okay, if they drop the ball bearing, how fast does it go to the bottom? Depending on the viscosity, it's going to be very slow, like molasses or honey, or very thick oil, or very fast. Vapor pressure is a special case, because vapor pressure, if you have, for example, an enclosed chamber. So we have an enclosed chamber. We have a beaker of water in here, and we keep it in that evacuated chamber. Eventually, what will happen is that that beaker of water will start vaporizing, going to the vapor state because it's at room temperature. And when it does that, it creates a certain vapor within that chamber. So the vapor pressure is how much of that vapor is in that chamber. Of course, that's related to the intermolecular forces. If the intermolecular forces are strong, then that chemical doesn't want to go into the gas phase very easily because it wants to stick to each other. So for strong intermolecular force, and this is the only property in which it's opposite, the vapor pressure is low. Okay. Weak intermolecular forces, the vapor pressure is high. That's why if you have like nail polish remover is one of those chemicals that has small intermolecular force. If you open it up, you can get a whiff of that easily. Okay. So let's move on. This is an example of vapor pressure. Here we have strong intermolecular force. So it doesn't want to go into the gas phase because it wants to stick to each other. Here we have weak intermolecular force. So it doesn't want to stay together. You can easily pry them apart. And so there's more chemical in the gas phase. So that's a good drawing of the differences in intermolecular force as it relates to vapor pressure. Here's another chart. You guys will see this a lot in your upper division. It basically tells you as we raise the temperature, the vapor pressure increases. And that makes sense because what will happen is that we loosen the intermolecular force between the chemicals, so it wants to go into the gas phase more easily. Clear that. And this is a movie that sort of explains that. I'm running out of time, so you guys should just watch it in the PowerPoint. But it basically gives you a more thorough explanation of vapor pressure, boiling point, and heats of vaporization. Okay, so again, a review on polarity. Let's, in this last 15 minutes, talk about the different types of intermolecular force. Ion dipole. Look at the size of these guys. It's very small. Very small means that it's got a greater attraction for the dipole because it's more concentrated. So if you look at the atomic radius, and this is the smallest one, This is the largest one. Look at the intermolecular force, or the enthalpy of hydration. That is the energy by which water is attracted to that ion. 515, the negative tells you it's exothermic. Just look at the absolute value. 515 is much greater than 263. In other words, the small ion is going to attract that water more efficiently than the big ion. So in this particular case, intermolecular forces increases with the size of the ion. Smaller is stronger, in other words. Dipole. We're looking at polarity. The polarity is the difference in electronegativity. Remember? So nitrogen is nonpolar. Silicon tetrahydride is nonpolar. Germanium tetrahydride is nonpolar. Bromine is nonpolar. But these chemicals down here are bigger. So if you look at the boiling point, this is a smaller chemical. They're all nonpolar, but the boiling point is increasing that way. This is the lowest boiling point. This is the largest boiling point. Okay. Now compare these to similar chemicals with about the same size. These chemicals are polar. Look at the intermolecular force. This 196 is lower than 192. They're still pretty low, but the fact that CO is polar means that it's got stronger intermolecular force. Look at bromine, which is 59, compared to ICl, which is 97. Again, they're about the same size. This chemical, however, over here is nonpolar. This chemical is polar. So just based on polarity, you've got stronger intermolecular forces. This is induced dipole. Let me try and explain to you what this means. Induced dipole arise because, first of all, the chemical is nonpolar. But this is true. You get this force, this lower intermolecular force is true for all chemicals with electrons. As long as an electron exists in the chemical, it has London dispersion force. But it's most significant for nonpolar chemicals. That's the key. Because for nonpolar chemical, this is the only force they have. So let me try and explain the mechanism. If you've got a chemical, it's got electrons. And those electrons are going to be buzzing around the nucleus. Every once in a while, these electrons are going to bunch up to one side. When they bunch up to one side, it creates what we call an instantaneous dipole. Okay? It's much more significant at lower temperature, but still, the electrons will bunch up just because of randomness. When that happens, a nearby chemical will notice that there are electrons near its edge. And so those electrons near that edge will be repelled. And when they're repelled, this side becomes partially positive, this side becomes partially negative. So what you're doing is you're inducing a dipole just because of randomness. Okay, but it's much more significant at lower temperatures. So basically what you have is like a wave in a sporting event. Once you get the wave going, then it sort of takes on a momentum on itself. Well, once these electrons start moving to one end, and all you need is to get it started, then everything sort of trickles down. And so that's London dispersion force, which we call LDF, London dispersion force, or sometimes we just call it dispersion force. Okay, or sometimes we call it van der Waals force. We have different names for the same thing. It's most significant for large chemicals. Why for large chemicals? Because for large chemicals, the electrons are all the way out here. So they're loosely held by the nucleus, by the protons. And so they could be polarized. That is, it could be distorted to a greater degree. So the ease by which the electron cloud can be distorted, larger the atom size, the greater the ease of polarization. So when you look at this, you can see that atomic size goes up this way, atomic size goes up this way. Both of these classifications of chemicals are non-polar. But look at the boiling point. Oops, sorry. Look at the boiling point. It's not showing it. I wonder why. Well, I think it shows it in the next slide, right there. The boiling point shows that it goes up significantly for larger chemicals. In fact, I2, you guys, I think, work with this, is a solid at room temperature. So even though it only has London dispersion force, its London dispersion force is much more significant than the dipole-dipole force of, say, a chemical like a liquid, like water. Okay, look at the halogens. The bigger the atomic size, the higher the boiling point, because it's much more easily polarizable. Xenon's 166.1, by the way. Then we come up to our last force, and I've already talked about this before. This is called hydrogen bonding. Take a look at this chart, okay? H2TE has a higher boiling point than H2SE and H2S. And this increase in boiling point has to do with size. Tellurium is a bigger atom than selenium, which is a bigger atom than sulfur. So it makes sense that its boiling point is going to be higher. Likewise with the carbon family, carbon, CH4, SiH4, GeH4, SnH4. These are all nonpolar. But tin is a bigger atom, so its intermolecular forces is bigger because of London dispersion force. You would expect, based on this trend right here, that water, if we follow this trend, H2O, would actually have a boiling point of negative 100 degrees Celsius. Yet water doesn't go down to negative 100, it actually goes up to positive 100. Why is that? Well, it's due to hydrogen bonding, okay? Here's the trend. What happens is that instead of going down, it goes up. So with F, so does NH3, but not with CH4. And you know what all these atoms, oxygen, nitrogen, fluorine, have in common? As well as hydrochloric acid. Hydrochloric acid actually doesn't follow the trend down, it goes up slightly. All these atoms, you recall, are electron hogs. These are our strongest electronegative elements. What happens is that because they are so strong for electrons, okay, since these are so strong for electrons, that their property doesn't go down, it actually goes up like that. And it comes from what we call hydrogen bonding. So let me show you how that works. This might be fluorine or nitrogen or oxygen. It's attracted to hydrogen, it's bonded to hydrogen. Because it's such a strong electronegative element, then almost all the electron density is going towards that very electron rich atom. And so I like to draw my electron cloud like that. What essentially happens is that it rips the electron density of that hydrogen. So what is a hydrogen atom made of? It's a proton and an electron. Since the electrons are all drawn away from the nucleus, then the proton is exposed. And because it's exposed, it's got a very high partially positive side. It therefore is going to be attracted to a nearby chemical that has a very strong attraction for electrons, okay? A nearby polar chemical, and that attraction between this naked hydrogen with its electron strip and this very electronegative element X is called hydrogen bonding. That's hydrogen bonding. That's the mechanism of hydrogen bonding. And that extra glue allows water not to be a gas at room temperature with a boiling point of negative 100, but a liquid at room temperature with a boiling point of positive 100. Without hydrogen bonding, the world as we know it would not exist. Everything would be in the gas phase. Okay, so I'm just going to wrap this up right here in terms of hydrogen bonding, and then I'll stop there. Okay, the integrity of the chemicals in our body, like the protein structure or DNA, is based on hydrogen bonding. The globular structure of proteins is because of hydrogen bonding. The way DNA unzips and zips is due to the base pair hydrogen bonding. And so hydrogen bonding is an important glue that is added on and gives the chemical added strength. Okay, so I'm going to end there. I'll probably pick this up next time. And so the question here in this particular slide is, which chemical exhibit hydrogen bonding? And what you need to look for is a hydrogen attached to an electronegative element. And that electronegative element is oxygen, nitrogen, fluorine, or chlorine. If you see that in the structural motif in these compounds, then it can have hydrogen bonding. Okay, and that's a quick illustration of that. So I'm going to stop there and wrap this up next time. But this was a pretty full discussion that I would usually have in class. We're talking about intermolecular forces that goes back to the geometry of a chemical. Okay, so I'll stop there. And for those of you in lab, I will see you in the other side at 3:30, because that's when it's sort of set up, and then show you what to do with that lab. Okay, and let me review for you the different intermolecular forces. We have something called LDF, and this is also called London dispersion force, also called dispersion force, also called van der Waals. Don't ask me why it has so many names, but these are the different ways that this particular force is categorized. This force arises it's prevalent for nonpolar chemicals, but all chemicals have London dispersion force. And the reason why all chemicals have London dispersion force is because all chemicals have electrons. If there are electrons in a compound, then you have London dispersion force. And no compound out there does not have electrons. And even as an ion, it still has electrons, but they're not so important for ions, because for ions, then you have a different type of intermolecular forces. But for neutral chemicals, all chemicals have London dispersion force. For nonpolar chemical, it's the most important force, because that's the only force that's available for nonpolar. For polar, you have London dispersion force and dipole-dipole. The way London dispersion force works is that you have a chemical, okay? Even if it's a noble gas, for example, this is the nucleus, this is the way the electrons are sort of buzzing around the nucleus, okay? Remember that we describe electron as a probability function, but we can still visualize it as a cloud. And what happens is that if it's near another chemical, and this might be two noble gases, and these things are sitting very close to each other, then every once in a while, the electrons, okay, are going to bunch up to one side. And so we have what we call an instantaneous dipole, because when the electrons sort of bunch up in this side, then this side is partially negative, and then where they're lacking, it's partially positive. But that automatically influences its neighbor. The neighbor with its electrons sees that there's a bunching up of electrons on this side, and so these electrons closest the neighbor are repelled by it, because remember, like charges are going to be repelled from each other. And so what happens is that if the electrons are influenced by its neighbor, then this side now becomes partially positive and this side becomes partially negative. The partially positive and the partially negative are going to be attracted to each other. Well, going down the line, this the second atom now has a partially negative on this side, and that's going to influence its other neighbor. And so what you have is like a wave. If you've been to the Q, I don't know what they're calling it these days, but back in the days when the Padres were winning, you would see the waves, and someone would basically be at the loge level and trying to rile up the fans to get the wave going. Well, that's kind of similar to what's going on here. All it takes is one atom, one element to kind of like rile up everyone else. And then what you have is a trickle down effect where these things are going to have an instantaneous dipole. So we have an instantaneous dipole, and then it's going to induce a dipole on its neighbor. And then that neighbor, now that it's sort of like having a dipole because it's induced from another element or molecule, is going to create its own dipole, and then it influences or induce its neighbor. So that's the way London dispersion force works. And because nonpolar chemicals only have these types of forces, that is going to be the strongest intermolecular forces that it possesses. Okay. In fact, these forces could be so strong that it can overcome dipole-dipole interaction or even hydrogen bonding. A classic example is I2. You know that I2, which is a diatomic chemical, has two iodines on it. And you guys have already seen the properties of I2. I2 is a solid at room temperature. If it's a solid at room temperature, it means that the atoms, the elements are sticking together, and they're sticking together because there's a lot of strong glue holding it together. If it had weak intermolecular force, it would be a gas at room temperature. The fact that it's a solid at room temperature means that it has strong intermolecular force. But it doesn't take very much energy to take I2 solid and get it into the I2 gas. Okay? And what happens is that it goes to the gas directly. We say it sublimes because it goes from a solid to a gas. It doesn't go through the liquid state. But the fact that I2 is a solid at room temperature means that the intermolecular forces for that chemical is huge. And why is it large compared to some other chemical? Because iodine, if you look at the iodine element in the periodic table, you see that it's a big atom. And because it has a big atom, it has a lot of electrons in the outermost shell. The further out the electrons are from the nucleus, the less tightly they're held, the more likely they're going to be able to do this instantaneous dipole. And when they do that, then they can influence its neighbor to stick together. So that's London dispersion force. Then we have dipole-dipole. And dipole-dipole is going to be most important for polar chemicals. Remember, polar chemicals not only have dipole-dipole, but they also have London dispersion force. That's dipole-dipole is just another glue, another force on top of London dispersion force. But the way dipole-dipole works is that if you're polar, then your electron cloud is going to be distorted. One part of the chemical is going to be, say, partially positive. The other part is going to be partially negative. And the part that's partially negative is going to be the side that's drawing the electrons towards itself. Because now you have some sort of like a magnet situation, okay? Negative here, positive here. Then another chemical that's polar nearby is going to orientate itself so that the positive end is going to be attracted to the negative end. So it's like having a whole bunch of bar magnets together. And you know that when you put a whole bunch of bar magnets together, the north and the north are not going to attract. The north and the south poles of a magnet will attract, and they're going to orientate themselves so that it's positive, negative, negative, positive, negative, positive, negative, positive. It's going to be a situation like this. They're going to just orientate, and that's the force that holds it together. Okay, that's dipole, dipole, because now these chemicals are thought of as like magnets. And these are most prevalent for polar chemicals. But remember, polar chemicals also have London dispersion force. Then the last force that we studied is hydrogen bonding. And hydrogen bonding arises because hydrogen is bonded to a very stingy element. We'll call that element X. And X can only be one of four. It can be fluorine, it can be nitrogen, it can be oxygen, and sometimes chlorine. And the reason why sometimes chlorine is because chlorine is large. And because it's large compared to fluorine, then the electrons are going to be further out. And so the electrons are not going to be influenced by the nucleus as, more as efficient as fluorine, in which the electrons are close to the nucleus. Okay? Because fluorine is small, the electrons are going to be more influenced by the nucleus where the protons are, and that's why the electronegativity for fluorine is the largest. It has an electronegative value of 4.0. Oxygen is about 3.5, nitrogen's about 3.0, and chlorine's about 3.0 as well. And that's because it has the most number of protons for for the same shell. Okay, remember, as you go from left to right on the periodic table, we have something called Z effective increasing. That is, the number of protons are going to increase within the nucleus, but the electron shell is the same. So it's going to draw that electron cloud closer in. So that's why fluorine is going to be the smallest. It also has the highest ionization energy. That is, you can't remove those electrons. And it's going to have the highest electronegativity. The way hydrogen bonding works is that you have a hydrogen here. It's got a proton. You've got an electronegative element here. Okay, we'll call that X because X can be one of these. And it's going to draw its electrons. It's going to draw its electrons over here. And so what happens is that this side, let me change my pen, is going to be mostly negative, big part negative. It's like dipole, but it's even greater than dipole. That's why we give it a special name called hydrogen bonding. Whereas this proton right here, now it's going to be naked because it doesn't have electrons out here. It doesn't have electrons out here to kind of like screen it. Because it's now exposed, then another electronegative element, maybe within the same chemical, okay, is going to see that proton. And because it has a very huge partially negative sign, it's going to be attracted to it. That attraction between this proton in a chemical that has this type of motif and this element right here that's very electronegative is what we call hydrogen bonding. Okay, that's what we call hydrogen bonding. We give it a special name because it's specific for hydrogen that is attached to these atoms. It's a form of dipole, but in a bigger sense because the fact that hydrogen is a very small atom, and when it loses its electrons, then that atom only has the proton left. It doesn't really lose it, but the electrons tend to reside more towards the electronegative element. That's hydrogen bonding. And always look for OH group, oxygen, hydrogen, because that automatically gives you hydrogen bonding. Look for NH group, definitely HF, but if you notice, HF can't really be in a very complex structure because hydrogen can only have one bond, and in general, fluorine only has one bond as well. So you're not going to have something like HF and then fluorine attached to something else, because when you do that, then you give fluorine two bonds, and fluorine doesn't like to do that. So HF is probably the one chemical in which you see hydrogen bonding, in which hydrogen is attached to fluorine. And then you have another chemical, H and Cl. But these are the most important characteristics that you want to look for in a chemical, and that'll have hydrogen bonding. If you have a chemical that has hydrogen bonding, it's automatically polar. Okay, if a chemical has hydrogen bonding, it's automatically polar, which means that it has dipole-dipole as well on top of hydrogen bonding. And then, of course, all chemicals have London dispersion force. Okay, so let me just make that clear. London dispersion force is the weakest, followed by dipole-dipole, followed by hydrogen bonding. Now, there are more intermolecular forces out there, but these are the main ones. If you've got hydrogen bonding, you better check mark dipole-dipole and London dispersion force. If you don't have hydrogen bonding but it's polar, then you also need to check off London dispersion force. If the chemical is nonpolar, then the only force that you have available is London dispersion force. So I hope that's clear. Okay, I hope that's clear in terms of what's going on. So let me go ahead and continue from where we start off. That was just like a review so that we bring everything together from what we talked about last time. So this is again the chart that shows how the boiling point, which is one of the properties that you can use to test for intermolecular forces. The higher the boiling point, the stronger the intermolecular forces for the chemical. And here you can see SNH4 has a higher boiling point than GE. This should be GeH4, okay? And the reason why that is because this particular chemical, these are all nonpolar, by the way. These particular chemicals are, tin is a bigger atom than uranium. And so what happens is that the intermolecular forces decrease the smaller the size. Then you also have antimony, H3. These chemicals now are polar, but they also have London dispersion force. Okay, they not only have dipole-dipole, but they also have London dispersion force. But remember, polarity, difference in electronegativity or electronegativity of an atom gets smaller as you go down the periodic table. So this chemical will be less polar than this chemical just because the electronegativity of antimony is less than the electronegativity of arsenic, which is less than the electronegativity than phosphorus. Okay, but what happens is that, let me clear this real quick. You see that trend in all these families in which a second element has hydrogen attached, but look what happens to the boiling point. Remember that the boiling point is a gauge of intermolecular forces. Look what happens when these hydrogens are now attached to these electronegative elements. Even chlorine. So you can see this is the halogen right here. Change my pen. This is the halogen right here. Where is that? Yeah, here. This is the halogen. Oops, let me get a pen that's more distinct. Let's try blue. This is the halogen right here. Bromine goes down, but look, chlorine goes slightly up. Not a lot, but it does go up. It breaks that trend. And then fluorine goes way up. Okay. So this just tells you the magnitude of hydrogen bonding right there. It's between 10 and 40 kilojoules per mole. And again, nitrogen, oxygen, fluorine, and chlorine are considered chemicals that exhibit hydrogen bonding. Okay, so we owe a great deal to hydrogen bonding in terms of life as we know it. Without hydrogen bonding, the proteins in our body would not function, because the way the protein works is they have a specific shape, and the shape is influenced by, some of you already know this, the primary, secondary, tertiary, and quaternary structure. And the tertiary structure is the way the hydrogen bonding folds that protein to have its globular shape, which is the ternary structure. So without hydrogen bonding, it would not have the shape it have, and then it would not function the way it does. And then, of course, DNA and RNA works on the double helix, especially DNA, and the way it unzips and unzips is through the base pair, and the base pairs are held together by hydrogen bonding. So here's an example of, of what's happening to the base pair. These things are hold on. Hydrogen bonding is weak enough that you can break it and then reform it. Okay, it's kind of like Velcro. Velcro is kind of neat, especially when kids can't tie their shoelace, because then you can just unzip it and then zip it. It's a convenient way. So hydrogen bonding is kind of like the Velcro of nature. And here it is shown in the double helix of proteins. Or not double helix, but the helical structure of proteins, sorry. So this is, again, a summary of some of the forces that you have, okay? It tells you how to interpret these things. So I'm just gonna go through by that. So this is an exercise I usually do with class if we were holding it in a classroom. And I would just take a look at this, study it for a moment, and tell me which chemical has this X hydrogen motif. Because if it has the X hydrogen motif, then it's got hydrogen bonding. Okay, and it also has, automatically, it'll have dipole, and London dispersion force, automatically. If it doesn't have that X hydrogen motif, look for whether the chemical is polar or non-polar. Because if it's polar, then it will have the dipole, and London dispersion force. If it's non-polar, then all it has is London dispersion force. Okay, so that's how you break this thing down. So if you look over here, this chemical, you wouldn't know it, but it has, well, you would know it if you work out the structure, which you guys will be able to do after today's lab. You can see that this chemical is nonpolar. There are 2 carbons, 2 central atoms, carbons, and all the terminal atoms, hydrogens, are the same. So it's perfectly symmetric. It's nonpolar. The only force available for this chemical is called ethane is London dispersion force. You see this motif right here? That's hydrogen bonding automatically. OH, hydrogen bonding. So the forces available for that chemical is hydrogen bonding, dipole, and London dispersion force. But hydrogen bonding is going to be the most greatest, the strongest glue holding these chemicals together. Here, you might not know this structure, but whenever you have a CH3, whether you write a CH3 as H3C or CH3, the reason we write it as H3C is because we want to illustrate that there are 3 hydrogens connected to that carbon, or that there are 3 hydrogens connected to that carbon. So whether we write it this way or this way, it's the same thing. It's just a different orientation. So there's a CH3 group. This right here tells you that this carbon is a double bonded oxygen, and then it's attached to a nitrogen. And then there's this nitrogen that has 2 hydrogens attached. Here it is right here, an H. That tells you it's got hydrogen bonding, okay? So it not only has hydrogen bonding, it has dipole, and London dispersion force. This chemical over here, now we have both hydrogen and fluorine, but notice they are not bonded to each other. This chemical, let me clear my screen, okay? This chemical will look like this, carbon. Again, this thing is called a methyl group. This right here is called a methyl. So when I say methyl, I mean these structural motif. This is a methyl group that has an OH. This is a methyl group that has fluorine attached to it, like that. But the fluorines are not attached to the hydrogen, so there are no hydrogen bondings here. Okay, here you see this motif. This is acetic acid. You guys should learn the structure of acetic acid because it's a very common chemical, and we use it a lot in chemistry examples. Here's your OH group. This right here is ethanol. This is the drinking type of alcohol, by the way. The alcohol that you can only consume is this guy. Again, you can see how common that methyl group is to a lot of organic chemicals. And then you have this right here, OH. So you can consume this, but don't consume any other alcohol. In fact, your alcohol beverage will only have this type of alcohol. This is methanol. And what people have done in the past is that they would not have enough ethanol, that's what this chemical is called, to make their moonshine. So they would spike it with methanol and then sell it. And methanol is a poison. If you consume large quantity of methanol, it will first blind you because it reacts with the chemicals in your eyes, your optic nerve, and it blinds you. It eventually will kill you. So hear a lot of stories like in third world countries where they're trying to make moonshine, and then they're not smart enough to know that you can't substitute the alcohol. So they might put rubbing alcohol, which is one more carbon compared to that. It's called propanol, or they might put methanol. And you hear about death because of that. Your body can't metabolize it. When you metabolize ethanol, you actually convert it to acetic acid. This group is going to get oxidized. You get an oxygen in here. Those two hydrogens will be eliminated. And you guys can consume acetic acid in mild quantities. That's what vinegar is. But your body actually creates it if it has a large quantity of ethanol. And in that particular case, what will happen is that the metabolism of ethanol will go to acetic acid. And that's why drunk people smell like vinegar, because they get acetic acid excreting. On the other hand, if you consume methanol, it'll convert it to this alcohol, it'll convert it to this acid, which is formic acid. Okay, it's formic acid. Formic acid, by the way, is the same chemical that fire ants excrete, and it burns. I see something in the chat. Can you please repeat the prior one? Can you tell me quickly what, I wasn't looking at my chat. I was sort of involved in that. So what part should I repeat so that I can be clear? Yes, Barry, acetic acid is only 5%. It's a very low quantity in vinegar. In fact, I think your last experiment has to do with titration of vinegar so that you can calculate the percent acetic acid in vinegar. Okay, so Sharon, if you can tell me what part to repeat, I can do that because I see there's something.
Professor, it's about the boiling point. You talked earlier that hydrogen fluoride, hydrogen chloride, antimony, germanium. Can you please repeat the part one? Sorry for the inconvenience.
Okay. Let me clear this real quick and then go back. The boiling point reflects intermolecular forces. So the higher the boiling point, the stronger the intermolecular forces. And this temperature right here, this is the boiling point temperature. So you can see that these chemicals over here have higher boiling point compared to their counterpart. If you look at the periodic table, tellurium is below selenium, which is below sulfur. If you look at the periodic table, antimony is below arsenic, which is below phosphorus, and then nitrogen's up here. So these atoms down here, these atoms over here, are going to be larger. Because they're larger, they have stronger intermolecular forces. Because they have stronger intermolecular forces, they have higher boiling point. And so as they get smaller, the boiling point decreases because they have weaker intermolecular forces. So it's going to take less energy, a lower temperature to separate them apart, to convert it from a liquid to a gas, until we get to chemicals that have an added glue. And that added glue makes them stick together more efficiently, so the boiling point goes way up. Okay, that's basically what I was saying about boiling points. Later on, we're going to see that you can gauge how strong intermolecular forces are for other chemicals just based on the properties we can measure. Properties we can measure are like boiling point, vapor pressure, melting point, heats of vaporization. All this reflects how these chemicals are glued to each other, how these things are attached to each other. Okay, so that's what I wanted to make. That's the point I was trying to make in this particular discussion. And it's important to know, make sure you know that, because that's how you guys are going to be tested. I'll give you some properties and I'll ask you, based on these properties, these chemicals, this has the highest boiling point. Which among these chemicals is going to have the strongest intermolecular forces? Or I might give you just the chemical formula, and you should know that, oh yeah, this chemical is polar, this chemical is non-polar, this chemical is going to have two added glue put together. It's going to have stronger intermolecular forces, therefore it's going to have a higher melting point. Those are the connections that you guys want to derive from this discussion. How the intermolecular force that operates at the atomic level manifests itself into the properties that we can measure: boiling point, melting point, heats of vaporization, how much heat it will take to melt an item, things like that. Okay, so that basically is why that's sort of important. So let me go ahead and finish this up, okay, because I don't really want to dwell a lot on these things, because I'm just sort of wrapping this particular section up. So let me clear this. This has, like I said, ethanol has OH, so it's going to have hydrogen bonding. This right here is this chemical right here. Notice that there's a methyl group here and a methyl group here. So we draw it this way. See the methyl group structural motif? This oxygen has a lone pair. That would be the Lewis structure. But you have oxygen, you have hydrogen, but oxygen's not bonded to the hydrogen. So there are no hydrogen bonding here, no hydrogen bonding. But it is polar. It is polar. Why? Because if you look at the terminal atoms, these right here are all terminal atoms. That is, they come at the end of a structure. These are all terminal atoms right here. These are all terminal atoms right here, and they look identical, but that also is a terminal atom, and that's not identical to oxygen. Because they have different terminal atoms, it's going to be asymmetric, it's going to be polar. And then, of course, we have this guy right here, and that is this structure right here. Again, it's a chemical that has, that is trigonoplanar. It's got an oxygen and a hydrogen, but no hydrogen bonding here, but it is a polar chemical. Remember, once I say it's polar, automatically in your mind, oh yeah, polar, dipole, dipole, also has London dispersion force. So please remember that. And that's because, and these are the structures. Let me clear this real quick. This is a summary of what we just did. Okay. So let me move on. So this is a typical question I usually have. I'll give you these formula, and you have to check off whether first determine whether it's polar or non-polar. That's the first thing that you want to do before anything else. Because once you've established that, then you can tell me what the type of forces are. We've already seen this. This is ethane. It's non-polar. We've already seen this. This is methanol. It's polar. We've seen this. You see that This chemical right here is going to look like this. It's got a methyl group, but the last attachment is a fluorine. It's nonpolar. Sorry, it's polar because the terminal atoms are not identical. This chemical, you can see that it's got oxygen in the center and CH3 group here. But if you remember, the oxygen has lone pairs. If you drew the Lewis structure, it automatically becomes polar because the central atom has lone pairs. If in the structure any central atom has a lone pair, then it's automatically polar. It makes this CH3 group bent because the internal structure of this guy is tetrahedral. The architectural structure of this oxygen, which is our main central atom, is tetrahedral. It makes it polar. Ammonia is definitely polar. And this guy, you see how you got fluorine here and fluorine here. So the terminal atoms are the same, but the two central atoms are not identical. So this is polar. So once we do that, then it's easy enough to figure out, let me erase this real quick, what the forces are. When it's polar, it's got dipole-dipole. By the way, all these chemicals have London dispersion force. When it's polar, it's got dipole-dipole automatically, okay? Hydrogen bonding, you're looking for the electronegative element connected to a hydrogen. Hey, that's this right here. That's that. Not this, not this. Hey, that's this right here. These are the two chemicals that have hydrogen bonding. Okay, so that's how you do the problem set like that. It doesn't take a lot of um, time to figure this out. You just have to make sure that you approach it with the correct strategy. And the correct strategy is first determine whether it's polar or non-polar. Okay, then once you figure that out, automatically all will have London dispersion force. Only polar chemical will have dipole-dipole. And then you look for the hydrogen electronegativity element motif. Once you find that, then it also has hydrogen bonding. Um, but remember, once you check hydrogen bonding, you better check the rest of these as well. So let me move on. Let me clear this real quick. And that's the answer. Here's another question. And the question is, what is the highest intermolecular forces for these chemicals? And the highest are going to be the following. It's going to be hydrogen bonding is the strongest, studied by dipole-dipole, followed by London dispersion force. But if you've got an ionic compound, then you also have ion-dipole interaction, or some sort of ionic interaction. And so this question has to do, identify the dominant intermolecular force for each of the following substance. Select the dominant intermolecular force and select the substance with the higher boiling point. The higher boiling point is going to be the chemical with the most dominating intermolecular force. So when we look at both of these, this is ionic, this is covalent. How do you know? This has a metal. Whenever there's a metal involved in the formula, it's ionic, okay? This has two nonmetals, but the two nonmetals are not the same. It's covalent, it's a compound. So this will have, it's polar, just like ammonia. And so it's got dipole-dipole and London dispersion force. This is ionic, so it's gonna have London dispersion force, but it also has something called ion dipole. So let me go ahead and clear that. Okay, and that's exactly what you see here. You got ion dipole. That's what is holding these things together. The other one's got dipole London dispersion. This one will have the higher boiling point. Ionic compounds will always have higher boiling point if you have it in its pure states. That's why ionic compounds are called salts. Salts, again, like sodium chloride is a salt, and it takes a lot of temperature, a lot of energy to melt a salt. Okay, you can dissolve it in water, but if you just take pure sodium chloride and you try and get it to its liquid state, so you have molten salt, that's a lot of, you need high temperatures to do that. If you take a look at this, they both have hydrogen bonding, but this is a bigger chemical, okay? So both have hydrogen bonding, both are polar, and both have London dispersion force. But because this is bigger, its London dispersion force is going to be much more substantial. Here, you have hydrogen bonding here. You do not have hydrogen bonding here. So this is just polar. This on top of hydrogen bonding is also dipole-dipole London dispersion force. Here, hexane and cyclohexane. Hexane has 6 carbons. 1, 2, 3, 4, 5, 6. Cyclohexane has 6 carbons. Remember I showed you that in chemistry, we represent carbons in this notation as the Ben in the line or the N in the line. So this has 6 carbons, 1, 2, 3, 4, 5, 6. This has 6 carbons. And because carbon always has 4 bonds, there's implied hydrogens in these things. There's 3 here, there's 2 here, there's 2 here, there's 2 here, there's 2 here, and there's 3 here. Okay, we just don't write it. Here, each of these have 2 hydrogens, and I'm not putting the H's, I'm just showing you the bonds that are coming off those carbons. But this is more compact. This is more compact. This is more stretched out. So if you look at a compact, which would mean that the electrons are tightly held or compactly held, versus something like this, which is going to be bigger, then again, the bigger the chemical species, the stronger the London dispersion force. So these 2 chemicals are only nonpolar. So they only have London dispersion force, but this would have the higher boiling point because it's going to be stretched out to a greater degree. So let's see if we're right. Let me go ahead and clear this so that you guys can see. Here, exactly, that's what we said. Here, exactly, that's what we said. And here, exactly, that's what we said. Okay, more surface area, that's the key. So again, this is a summary, and then it manifests itself in the properties of water. You guys should read the properties of water. These are the many properties of water, or the many properties that we can measure. Let me just say that. The density of the substance, the surface tension, the capillary action. Capillary action has to do with whether a chemical will go up a straw or a tube. And you see that if you ever take a small capillary and you put it in water, you have a pool of water, automatically water will go up. That's how plants suck up water hundreds of feet up in the air. Okay. Heat of fusion, that's just the temperature, the energy you need to put in to melt a substance, or the energy you get out when a substance goes from the liquid to a solid. Heat of vaporization, that's just the energy you need to put in to vaporize a substance, or the energy you get back when a gas converts over to a liquid. Viscosity, that's just the resistance of flow. You already know about boiling point, melting point, and vapor pressure. These are properties that have their, their properties are influenced by their intermolecular forces, okay? So again, this is for water now. And these are for water because it's got hydrogen bonding and it's a small chemical. It's got remarkable properties. It's one of the, it has a low density in its solid form compared to the liquid form. Generally, that's not what happens. It's got capillary action. It's got the highest specific heat for small chemical. It's highly viscous compared to its size. Of course, the boiling point is very high, as well as the melting point. And the vapor pressure for water is generally low. Okay, here are some of their values in terms of these properties. But what I do next in these few slides, and you guys should read it because I want to move on to gas laws, um, is that water is a universal solvent because not only is it polar, but it can hydrogen bond. That's why a lot of things dissolves in water, and that's why we call it a universal solvent. Here, we see that in the solid form, ice is less dense than the liquid form. That's not true for most substance. For most substance, the solid form is more dense than the liquid form, and so it should sink. And why is that important? Imagine if ice was more dense than the liquid, then the ice would form at the bottom of a lake, and then the whole lake would easily freeze over because then the surface of the lake is going to be influenced to the temperature, the ambient temperature. By putting ice over water because it floats, it basically insulates the rest of the body of water underneath. It acts as an insulation layer. So what does that do? It allows the fact that because only the top layer freezes and then the bottom layer, although it's cold, won't freeze, you can have marine life. And the whole lake doesn't freeze over. It thaws out at the surface. So in terms of marine life in lakes and even in the polar caps, it's very important that ice have a lower density than liquid form. Okay, take a look at this real quick. I want to show you that indeed most solids will sink compared to its liquid. But if you take a look at ice, okay, you see that over here, see how that thing sort of sinks? Okay. Um, I'm sorry, but the video is sort of choppy. Whenever I do multimedia, it's always a very slow process. Here, ice floats. So that's the message here, is that for most substance, their solid form is more dense than the liquid form. Okay. Water also has a very huge surface tension, and that's important because then that's what causes the beating of water when it is exposed to a place called hydrophobic. Hydrophobic and hydrophilic, those are two words that you guys probably covered in your biology course. Philic means loving, okay? So if you're philic for something, okay, you probably heard the word is well, hydrophilic means water loving. Hydrophobic means water hating. So if you're hydrophilic, then you're going to have attracted to water. If you're hydrophobic, then you're going to repel water. And so what happens is that if you ever wax your car and it rains, you'll see that the rainwater sort of beads. And that's because the wax is non-polar, water is polar, and so they're hydrophobic to each other. Anyway, that's what the surface tension is here. Surface tension allows the water molecules to kind of like come together and form these beads because they're going to be attracted to each other. But if there's this particular item that the water droplets is attached to is non-polar, then it's not going to be attracted to it. That's why you see the beading. You also have capillary action. Water automatically gets drawn. And you see that with glass a lot because glass has silicon oxide group. And so the hydrogen in water can be attracted to the oxygen in silicon oxide in glass. And so that's what you see right here. Because the walls, the water wants to maximize its attractiveness to glass. It's going to be attracted to the glass, and then water is also attracted to itself. That's why you see a concave down attraction, because they're attracted to itself but also attracted to the glass. Anyway, there's two forces that are competing against each other. You have adhesive force and cohesive force. Adhesive force is the attraction for things that are not the same. Cohesive is the attraction for things that are the same. For water in glass, the adhesive force is stronger than the cohesive force, and so it goes up that channel. For mercury, however, remember mercury is a liquid. the cohesive force is greater than the adhesive force. That's why you will see mercury will have a concave down. If you ever put it in a tube, it'll look like that. Okay, if you ever have a mercury thermometer and you look inside, you see that it has a concave down. Anyway, uh, these are just other things. You guys should read this on your own. I'm just gonna go through this real quick. Heats of vaporization, one of the highest for water. And again, how does that manifest itself in the properties that we know? Uh, yes, exactly. Fear of water. Phobic is fear, and philic is like. So that's the property that you see if you guys look at the chat. Um, Heats of vaporization. Let me mention that real quick. When you when you exert yourself, if you've been doing a lot of exercising because you get stir crazy because everyone's confined at home, so you might be doing some sort of running in a park or some sort of exercising at home, then the way your body cools itself is it perspire, it sweats. But that itself is not the cooling process. When you perspire, there's water droplets on your skin. And as that water droplets evaporate, it's taking away 540 calories per gram. Remember that in order to take water from the liquid to the gas, it costs 540 calories. That's the heat of vaporization. That means that when the gas, it's removing that amount of energy, okay, when it goes from a liquid to a gas. When your perspiration expires from your skin and it evaporates, that's the cooling process. Okay, that's the cooling process, and that's how you cool yourself down. Uh, and then vapor pressure. Vapor pressure is interesting because vapor pressure is the lowest for strong intermolecular forces. It's just opposite the other. And let me try and explain that, okay? When you have weak intermolecular forces, you have the highest vapor pressure. When you have strong intermolecular force, you have the lowest vapor pressure. And let me try and explain that. When something evaporates, this is a beaker, and what will happen at room temperature is that the liquid form will eventually form and escape that interface, because some chemicals are just going to have a certain amount of energy that it can escape, and then it goes from a liquid to a gas. You can do this experiment. Take a beaker of water or a glass of water, put it out in your kitchen table overnight, and you see that the volume, if it's not humid, okay, if it's dry, if it's humid, then that's not going to work. But if it's dry, then you're going to see that water evaporate over time. Well, suppose you enclose this so that you're trapping the vapor. Well, the amount of gas in that chamber is the vapor pressure. Okay, you can measure the amount of pressure that the gas will exert in that environment. So you can see that the more likely it can evaporate. Is it more likely to evaporate? Because it has weak intermolecular forces. Then the more likely it'll go into the vapor phase, the greater the vapor pressure. So for weak intermolecular force, you're going to have high vapor pressure. When a chemical is very strong in terms of intermolecular force, then you get a very few vapor out here. And that's because it wants to be tied in the liquid. It's not going to be likely going into the gas phase. And when it does that, because of the strong intermolecular force, less vapor, lower vapor pressure. Okay. So hopefully you make that connection. And again, that's why intermolecular force, especially if you're going to medicine, okay, is so important, because the forces of in chemistry are found in nature, and the properties that you find in these compounds, these chemicals, the things around us, is can be understood if you know the intermolecular forces available. So again, that is why vapor pressure, here you have the vapor pressure of water, is going to be highest for chemicals that have the lowest boiling point. And this is just a summary of the heating cooling curve. Should I use this to kind of like show you about heats of vaporization, heats of fusion, okay, things like that. But I think we covered this back in chapter 3. And that pretty much takes care of chapter 12. Okay, that pretty much takes care of chapter 12. And so if you have questions on this, or as you're studying this, you guys have questions, make sure that you ask. Did we cover? Yes, we covered it in either in chapter 3 or in the part where we looked at matter and energy. And the reason why we covered that, the reason why I remember we covered that in chapter 3 or the early chapters, we did a calorimetry experiment in the lab. That is, we tried to figure out how much heat it would take for these substances. And so that was all that particular section. Okay, so go back and review that quickly, but it's basically this chapter just adds to the context of that particular chapter. Okay,